Hello, my name is Bobby Quinn. This is my video submission for part 23, tutorial number 2. In this short video, I will walk you through connecting to a database via Microsoft SQL Server Management Studio. I will show you the tables of the database created in this tutorial, as well as the database diagram, where I will enumerate the relationships between tables. I will then execute 2 queries as detailed in this tutorial, and will end the video with a simple query that allows us to visualize the spatial result of a query that includes wicket values for polygons. First, I will connect to the database server. Upon opening SQL Server Management Studio 2012, the user is greeted with a default pop-up which allows you to connect to a server of your choice. Here we will choose Database Engine and input the server name gis-db.usc.edu. With no other entries required, I click Connect to establish a connection to the USC GIST server. Once logged in, we are able to access the Object Explorer in the leftmost pane over here. You'll notice that Microsoft has chosen to model their Object Explorer like the familiar Windows file management system, even though you're using a relational database management system or RDBMS. Expanding the database folder reveals all of the databases currently residing on the server. I can type in the first few letters of my database, RobertAQ_T2, to quickly find my database within the tree. And there it is, and let's expand it. Expanding my database, we see 8 subfolders. For this video, we will only discuss the tables and database diagrams folders. Let's expand the tables folder. This database has 5 tables. The tables in the database are city, country, Great Lake, lake, and shore. Expanding one of these tables, we see the standard features for any new table created within SQL Management Server Studio. These subfolders include columns, keys, constraints, triggers, indexes, and statistics. Next, we'll take a look at the database diagram. Relationships in Microsoft SQL Server Management Studio can be visualized in a database diagram. In this diagram, we can see all 5 tables within my database. 4 of these tables have relationships to at least one other table, while the Great Lake table has no relationship established. Although the Great Lake table is not related to any other table, it contains wickets for the Great Lakes polygons. Following the import of the instructor-provided Great Lake MDB access file, these wickets were copied into the newly made columns titled Wicket and Shape within the Lake table. The relationship between tables are as follows. A one-to-many relationship between country and lake tables tied on country.name as the primary key and lake.inCountry as the foreign key. A one-to-many relationship between the country and city tables tied on country.name as the primary key and city.inCountry as the foreign key. A one-to-many relationship between the country and shore tables tied on country.name as the primary key and shore.inCountry as the foreign key. A one-to-many relationship between the lake and shore tables tied on lake.name as the primary key and shore.onLake as the foreign key. And finally, a many-to-many relationship between the country and lake table using the shore table as an intersection table. Let's take a look at the lake and shore tables in a split horizontal tab group view. In step 18 of this tutorial, we created a new table, shore, that was to be used as an intersection table to establish a many-to-many relationship between the country and lake tables. The shore table contains 3 columns, in country, on lake, and shoreline. In the shore table, both in country and on lake are both foreign keys that create the one-to-many relationships between the country and lake tables. In the second part of Part 18, we were asked with adding bathymetry data from the Great Lakes Wikipedia page into the lake table. As you can see, bathymetry was added for Lakes Erie, Heron, Ontario, and Superior. Additionally, we inserted shoreline links for each Great Lake by country into the shore table. Next, we will execute 2 simple queries that we were asked to create in this tutorial. The first query will allow us to display lakes in alphabetical order whose shores are both in Canada and the United States. In this query, we select the distinct lake names using the on-lake column from the shore table where the name appears twice in the table. This query method relies on the fact that if the lake name appears twice within the shore table, then it has a shore in both Canada and the US. This method is successful because column name in country in the shore table, which also happens to be the primary key, does not allow null values. So here you can see the first query results in the lakes by order alphabetical listing for each of the lakes that border both Canada and the US. The second query is a slight modification from the first query. This query allows us to display the amount of shoreline in the U.S. of all lakes whose shorelines are in both Canada and the United States, ordering results by linear distances descending. In this query, we add the column shoreline to the select clause, as well as an additional condition in the where clause where in country equals United States. We also change the order here to display results by shoreline values descending. The results are as you can see here. Lake Superior with shoreline 1000 is on top. Lake Ontario with 300 is on the bottom, with shoreline units descending. Finally, we'll take a look at the spatial result of a query that includes wicket values of the Great Lake polygons. You can see the wicket populated in the wicket column with the data type nvarchar, or national character varying. And the wicket. Fun fact, when the string length is set to maximum, as it is in the case of the wicket column of the lake table, the maximum storage size for that field is 2 gigabytes. The shape column stores the wicket as a geometry data type. SQL Server Management Studio as well as GIS use this field to generate digitized polygons. In this interface, those polygons can be seen in the Spatial Result tab of the Results page. So we'll open that up. Drag this up, and here you see the graphical representation of those polygons digitized on a map. This completes my video for part 23, tutorial number 2 for SSCI 582 Spatial Databases with Professor An Min Oo. Thank you for watching.